The Foundations of Geometry by David Hilbert. Chapter 3, The Theory of Proportion. Section 15, An Algebra of Segments based upon Pascal's Theorem. Pascal's theorem, which was demonstrated in the last section, puts us in a position to introduce into geometry a method of calculating with segments, in which all of the rules for calculating with real numbers remain valid without any modification. Instead of the word congruent and the sign for congruent, we make use in algebra of segments with the word equal and the sign equal. If A, B, and C are 3 points of a straight line, and if B lies between A and C, then we say C equal to AC is the sum of the two segments A equal AB and B equal BC. We indicate this by writing C is equal to A plus B. The segments A and B are said to be smaller than C, which fact we indicate by writing A is less than C, B is less than C. On the other hand, C is said to be larger than A and B, and we indicate this by writing C is greater than A and C is greater than B. From the linear axioms of congruence, axioms 4, 1 through 3, we easily see that for the above definition, the addition of segments, the associative law, A plus the quantity B plus C equal to the quantity A plus B plus C, as well as the commutative law, A plus B equals B plus A, is valid. In order to define geometrically the product of two segments A and B, we shall make use of the following construction. Select any convenient segment which, having been selected, shall remain constant throughout the discussion and denote the same by 1. Upon the one side of a right angle, lay off from the vertex O the segment 1, and also the segment B. Then from O, lay off upon the other side of the right angle the segment A. Join the extremities of the segments 1 and A by a straight line, and from the extremity of B draw a line parallel to this straight line. This parallel will cut off from the other side of the right angle a segment C. We call this segment C the product of the segments A and B, and indicate this relation by writing C is equal to A times B. We shall now demonstrate that for this definition of multiplication of segments, the commutative law A times B equals B times A holds. For this purpose, we construct in the above manner the product AB. Furthermore, lay off from O upon the first side, 1, of the right angle the segment A, and upon the other side, 2, the segment B. Connect by a straight line the extremity of the segment 1 with the extremity of B situated on 2, and draw through the endpoint of A on 1 a line parallel to this straight line. This parallel will determine by its intersection with the side 2 the segment BA. But because the two dotted lines are, by Pascal's theorem, parallel, the segment BA just found coincides with the segment AB previously constructed, and our proposition is established. In order to show that the associative law A times the quantity BC is equal to the quantity AB times C holds for multiplication of segments, we construct first of all the segment D equals BE, then DA, after that segment E equals BA, and finally EC. By virtue of Pascal's theorem, the extremities of the segments DA and EC coincide, as may be clearly seen from Figure 24. If now we apply the commutative law which we have just demonstrated, we obtain the above formula, which expresses the associative law for multiplication of two segments. Finally, the distributive law, A times the quantity B plus C equals A times B plus A times C, also holds for our algebra of segments. In order to demonstrate this, we construct the segments AB, AC, and A times the quantity B plus C, and draw through the extremity of the segment C a straight line parallel to the other side of the right angle. Figure 25. From the congruence of the two right-angled triangles, which are shaded in the figure, and the application of the theorem relating to the equality of the opposite sides of a parallelogram, the desired result follows. If A and B are any two arbitrary segments, there is always a segment A to be found such that C is equal to AB. This segment A is denoted by C divided by B and is called the quotient of C by B. The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Wrenholt. Programming and illustrations by Jim Wrenholt. 2019. Portrait of David Hilbert by Reida Wrenholt. Thank you for listening.